All right. So great to see everyone face to face after 2 years. So welcome here. So good afternoon. My name is Amita Manatunga. As chair of the Committee of Presidents of Statistical Societies, I am privileged to welcome you to this year's COPSS Award Ceremony and COPSS Distinguished Achievement Award and Lectureship. COPSS is an organization that represents 5 statistical societies: the American Statistical Association, the Eastern and Western North American regions of the International Biometric Society, the Institute of Mathematical Statistics, and the Statistical Society of Canada. COPSS works on common issues in our profession to improve inter-society communications. It also sponsors a number of prestigious awards in our profession. Today, we have the pleasure of announcing the winners of those awards, as well as to hear the COPSS Distinguished Achievement Lecture. COPSS consists of the presidents, past presidents, and president-elects of 5 societies. The COPSS works with the Friends of COPSS, listed here, as a way to broaden the discussion of common issues in our profession. The COPSS officers consist of myself, Maya Sternberg, and Lucy D'Agostino McGowan. Please join me in thanking Professors Brahma Mukherjee and Judy Wang for their outstanding leadership of COPSS for the last 3 years. Thank you. Thank you. Thank you, Judy, and thank you, Brahma. Today, we have 3 prestigious awards to be presented to our distinguished colleagues for their contributions towards our profession. These include Elizabeth L. Scott Award, President's Award, and COPSS Distinguished Achievement Award and Lectureship. Every other year, COPSS also sponsors other awards. For the next year, we are seeking nominations for the awards listed on this slide. We encourage you to nominate your colleagues and mentors for their contributions to be recognized. The deadline is December 15th of this year. I also want to acknowledge the COPSS Award Committee, chaired by Abdus Warhead, for their work last year. Members of the committee are listed on this slide. I want to acknowledge COPSS Diversity, Equity, and Inclusion Task Force, chaired by Alicia Karkuri. I would like to thank the committee for their contributions. Since 2019, this is the first year that we are meeting in person at the Joint Statistical Meeting. Last 2 years, the ceremony has been conducted virtually to honor awardees. Therefore, I would like to recognize 2020 and 2021 COPSS awardees today. So here is the list of 2020 awardees: Rena Fogel-Barber, Catherine Roeder. And the 2021 awardees recipients are Jeff Leake, Alicia Karikuri, David Danson, and Wing Hang Wong. If you are in the audience, please stand up so that we can recognize you. Let's give a big round of applause for the last 2 COPSS years honorees. The COPSS also inducted 9 emerging leaders in statistics to the COPSS leadership in 2021. If you are here today, please stand up so that you could be recognized. Thank you. Well, now we begin the presentation of this year's awards. Now I turn the podium over to Professor Richard Samworth from Cambridge University to present the 2022 COPSS Leadership Academy Award.
Thank you very much, Amita. So I'd like to begin by thanking my fellow members of the COPSS Leadership Academy Selection Committee. There's an awful lot of paperwork that goes with all the nominations associated with these nominations, so I'm really very grateful for all the hard work that they did in trying to make the fairest decisions possible. Okay, so the COPSS Leadership Academy aims to recognize early career statistical scientists who show evidence of and potential for leadership and who will help shape and strengthen the field. The award is open to all junior members of the international statistical community. An eligible candidate will have received a terminal statistically related degree up to 10 years prior to the award year. So we have 8 new awardees to announce tonight, or this afternoon. And I'm going to announce them 2 by 2. And as I do so, I'd like to invite them to come up the stage to receive their awards. But we'll hold off the applause until I've announced all 8. Okay? So, the first awardee is Shi Chen from New York University for notable contributions to statistical inference for distributed, online, and high-dimensional data, to stochastic optimization, and to statistical applications in business domains, for outstanding educational efforts to the next generation of business leaders, and for significant industrial impacts. And to Natalie Dean from Emory University for groundbreaking, high-impact work in the development of innovative study designs and analyses for evaluating novel vaccines and for wide-ranging public engagement and thought leadership during the COVID-19 pandemic. The next 2. Davina Durgana from Oxford University and Walk Free, in recognition of outstanding service through pioneering scientific research and policy communication to end human trafficking and advocacy efforts to encourage youth and women in STEM fields across the world. And Philip Ernst from Rice University for significant contributions of extraordinary merit to applied probability and mathematical statistics, particularly the resolution of the long-standing conjecture of Yule's nonsense correlation, outstanding teaching, and leadership. Pierre Jacob from ESSEC Business School for path-breaking contributions to Monte Carlo algorithms and Bayesian statistics, and for exemplary dedication as teacher and mentor. Unfortunately, Pierre is unable to be here today. And Christian Lum from Twitter for strong contributions to the study of algorithmic fairness and ethics in statistics and data science, for high-quality, high-impact collaboration and advocacy in social justice, and for leadership in maximizing our profession's openness and support of all members. To Lester Mackey from Microsoft Research for significant contributions to the theory and practice of statistical machine learning. And finally, to Betsy Ogburn from Johns Hopkins Bloomberg School of Public Health for creative methodological innovations in causal and network analysis, for contributions to education, for generous service to the profession and society, including leadership in addressing the COVID-19 pandemic. Let's thank all of the new awardees.
Thank you, Richard. It is my pleasure to invite upon stage Professor Rebecca Hubbard. Sorry. It is my pleasure to invite upon stage Professor Rebecca Hubbard from University of Pennsylvania School of Medicine to present the 22 Elizabeth L. Scott Award.
Thank you and good afternoon. It's my great pleasure to present the winner of this year's Elizabeth L. Scott Award. This award is presented in even number years, beginning in 1992, in recognition of the lifelong contributions of Elizabeth L. Scott, specifically towards fostering opportunities for women in statistical careers. It recognizes an individual who exemplifies the attributes of Dr. Scott, including her contributions to developing programs to support women in academic careers, to consistently and successfully mentoring women, to working to identify gender-based inequities in employment and eliminate those inequities, and to serving as a role model across a wide variety of domains. Elizabeth L. Scott was a researcher in statistics, astronomy, and weather modification. And in her honor, the Scott effect was named to describe observational bias in the study of galaxies. She used statistics to promote equal pay and equal opportunities for women in higher education. And she was co-chair of biostatistics and chair of statistics at the University of California, Berkeley. She was also the first woman president of the IMS. This is our 2022 award committee, and I'd like to recognize all of their contributions to the process of selecting an award winner. It was a very challenging process. We had a lot of really outstanding candidates, and I'd like to acknowledge the contributions of the committee. And the 2022 winner is Dr. Madhu Mazumdar from the Icahn School of Medicine at Mount Sinai, where she is professor of biostatistics in the Center for Biostatistics, Department of Population Health Science and Policy, and director of the Institute for Healthcare Delivery Science. Congratulations, Dr. Mazumdar. I'd like to take just a few moments to highlight some of her outstanding contributions which led to this award, specifically her leadership across a wide range of collaborative science domains. She's been a biostatistical leader across multiple institutions, created a team of staff biostatisticians at the Memorial Sloan Kettering Cancer Center. She established the Division of Biostatistics and Epidemiology at the Weill Cornell School of Medicine, and she developed the Institute for Healthcare Delivery Science at Mount Sinai. She has over 320 peer-reviewed papers, is the winner of a Team Science Award awarded across 4 research associations, and was elected as a fellow of the ASA in 2013. In addition to her outstanding leadership and research contributions, she has fostered opportunities for women, specifically in academic medicine and statistics. She's fostered opportunities for over 100 researchers, worked to address salary equity issues, raised funds for training programs specifically to increase diversity, equity, and inclusion, and has worked with the Clinical and Translational Sciences Centers to develop a framework for evaluating team scientists and engaging collaborative biostatisticians. I wanted to highlight just one of the many amazing quotes that we received in the nomination materials for Dr. Mazumdar. This one comes from Dr. Kristen Dams O'Connor, who said, "She is a mentor, a sponsor, and a champion of women, and she's often all 3 at once. It is difficult to imagine a woman in academic medicine who is more deserving of this honor." The citation for Dr. Mazumdar reads, "For serving as an outstanding role model of leadership and creating new leadership opportunities for statisticians, fostering opportunities in statistics and promoting statistical careers for diverse trainees, dedication to training and mentoring the next generation of statistical leaders, and excellence in team science research." Congratulations, Dr. Mazumdar.
So thank you, Dr. Hubbard, for that generous introduction, and thank you all for your time. I was very fortunate to be exposed to Dr. Scott's work very early in my career. In 1991, when I joined Sloan Kettering Cancer Center, I was asked to analyze the physician's salary at that center. Guided by Dr. Scott's salary kit that you just heard about, I was able to show that women physicians were paid less at that center, and the salary was adjusted. Seeing such early on the effect of regression analysis making change really inspired me, and I just got hooked to that line of work. So this is really a great honor to get this award with Dr. Scott's name on it. Thank you to the COPSS Scott Award Committee for choosing me. Thank you to all my mentees, some of whom I see in the audience. Thank you for working hard, being successful, and taking on leadership opportunities. Your success is the reason I'm getting this award. Thank you to my nominator, Dr. Jaya Sadgopan, Professor of Biostatistics at Rutgers School of Public Health. Dr. Sadgopan was very busy creating a new center for South Asian quantitative health and education, and being an associate dean for faculty development, but she found time in her busy schedule to write a strong nomination package for me. So thank you, Jaya. Thank you to my family for always prioritizing my work, and thank you all for keeping academic women in your mind. Dr. Scott's work of many of the Scott awardees before me, and I'm sure many of you in this audience, academic women's position is much better than it was in Dr. Scott's time, but they are still not equal in many areas. So the work has to go on. Energized by this award, I'm certainly going to continue it, but I'm inviting you all to join and be mindful that the academic women are still having many vulnerable time points where their careers are sliding. Thanks to our Supreme Court, as you can see, that the women's right can fizzle away anytime. So be vigilant and keep working on improving the status of academic women. Thank you all.
Congratulations. Next is an award where the winner's name is confidential until now. So to reveal the secret, I invite upon stage Professor Tianxi Kai from Harvard University.
The President's Award is presented annually to a young member of one of the participating societies of COPSS. The award is presented in recognition of outstanding contributions to the statistics profession. It can be a single contribution of extraordinary merit to the profession of statistics, or an outstanding aggregate of contributions to our profession. It's given to an individual who has not yet reached his or her 41st birthday during the calendar year of the award, or an individual who has not yet reached his or her 46th birthday during the calendar year, and received a terminal statistically related degree no more than 12 years prior to that year. So I would also like to thank my fellow committee members for all the hard work. And this year, the award goes to Daniela Waiton. She is Dorothy Guilford Endowed Chair of Mathematical Statistics. She's a professor in both the Department of Statistics and Biostatistics at the University of Washington. She is a hardcore Stanford graduate, receiving all her degrees from Stanford with her PhD in 2010. And she has made fundamental contributions to the field of statistical machine learning. She has made important contributions to the field of genomics and neuroscience, and she also made enormous work towards a translation of statistical ideas to a broader audience. I don't know if any of you has watched her NOVA documentary. If you haven't, I highly recommend. I was really moved and proud as a fellow statistician who watched her explaining the idea of statistics and pushing the field of statistics to really front and center to the broader audience. And her citation reads, "For bridging the gap between the questions that scientists are asking about their idea, the data and the statistical methods that are available to provide insightful answers, especially in the context of biomedical research. For developing flexible and interpretable approaches for modeling large-scale and high-dimensional data, and for the significant elevation of statistical science via successful translation of statistical ideas to a broader audience." Congratulations.
Winning this award is the honor of a lifetime for me. I'm pinching myself. And I have so many people to thank. First and foremost, my PhD advisor, Rob Tibshirani. He believed in me from day one and has never stopped. He taught me so much about being a statistician and a human. So to any grad students here today, I hope that you have the good fortune of finding yourself a PhD advisor who is as brilliant, funny, generous, and kind as Rob. Second, I want to thank the two departments that have provided me with an academic home and their unwavering support these past 12 years, University of Washington Statistics and University of Washington Biostatistics. They have supported me, no questions asked, and this has enabled me to follow my passions and pursue the questions I'm interested in. Special thanks to Patrick Hagerty, who nominated me for this award, and to Bruce Weir, the department chair who hired me and gave me tenure. And the secret behind my success is the absolutely fantastic set of PhD students who I've had the privilege of working with throughout my career. Ari Vorman, Keen Ming Tan, Shija Chen, Ashley Peterson, Sean Jewell, Lucy Gao, Yandi Shen, Yuchun Chen, Brian Martin, Anna Neufeld, and also my postdoc, Guo Yu. None of this would have been possible without their dedication, talent, and hard work. Every day I learn from them how to be a better statistician, a better advisor, and a better person. And so I share this award with all of them. And I've been lucky to work with brilliant collaborators who've made my research a joy. These include my colleague, Ali Chauget, my longtime friend, Jacob Bien, and my textbook co-author, Gareth James. What an amazing privilege to be friends with smart people who are willing to do research with me. I want to thank the statistical community that has made my career possible. I felt welcomed into this community ever since I arrived at my first JSM in Denver in 2008 as a third-year grad student. I want to especially thank the senior female statisticians who've provided me with mentoring and encouragement over the years and who have reminded me that I can do hard things. This includes Lisa Lavina, Bramar Mukherjee, Florentina Bunea, Francesca Domenici, and others. And I also want to thank Raphael Irizarry, Jeff Leake, and Paul Fernhead, who wrote letters in support of my nomination for this award. And finally, my husband, Ari, is here today. We started dating 20 years ago, well before my first T-test. Ari, it's been a wild ride, and there's no one I'd have rather spent it with. And along the way, we made some new friends. Our wonderful children, Tessa, Theo, and Otto, who are sitting in the second row and are still trying to figure out what I do for work. Tessa and Theo and Otto, you are and always will be my most important prizes. Thanks again to the award committee, the COPSS leadership team, and to the statistical community for this tremendous honor.
It is raining and thundering. So next, I would like to turn the podium to Professor Rebecca Dodge from Carnegie Mellon University to present the Distinguished Achievement Award and lectureship.
Good afternoon, everyone. I promise there is not a bowling alley upstairs. I checked. It's just the thunder. On behalf of the, let's see, let me get organized. On behalf of the Committee of Presidents of Statistical Societies and this year's selection committee, it's my distinct pleasure to present the 2022 Distinguished Achievement Award and Lecture. All right, what's the secret here? Great, thank you. Thank you.
You can go back. If you want to go back, say go back, please. Then on the back side they will do it.
Okay, great. So as some of you may know, this award originated in 1963 with the first award, the R.A. Fisher Award and Lectureship being given in 1964. It was renamed the Distinguished Achievement Award and Lectureship in 2020. The award and lectureship is a recognition of very high achievement and scholarship in statistical science and recognizes high significant impact of statistical methods on scientific investigations. I'd like to thank my partners in crime, the COPSS Distinguished Achievement Award and Selection Committee. This committee is on a 3-year rotation, so we always have some folks from before and after, and it was a real pleasure to work with everyone on this nomination. So thank you for your time. This year's COPSS Distinguished Achievement Award and Lectureship goes to, drumroll please, Nancy Reed. Nancy was nominated by Christian J. and Erica Moody from McGill. And the citation that they presented for Nancy was for pioneering contributions to statistical theory, in particular to likelihood inference, strong commitment to promotion of statistical thinking across a wide range of applications, outstanding service to statistical profession, and for being a role model and advocate and mentor to young statisticians. I think that John Weller said it best. He said that Nancy has contributed fundamental and path-breaking work in a wide range of statistical problems, including non-parametric estimation for survival data, applications of differential geometry to statistics, conditional inference, profile and composite likelihood methods, higher order asymptotic, and the list just goes on and on. And Nancy, of course, has been recognized many, many times, but I'd like to point out that she was the first woman to receive the COPSS President's Award in 1992. She is a Fellow of the Royal Society of Canada. She is an Officer of the Order of Canada. She is a member of the National Academy of Science. She is a Fellow of the Royal Society, and just this year she was nominated the Guy Medal in Gold. So these are just outstanding, outstanding achievements. So congratulations to Nancy. Please join me in welcoming her to the stage. So Nancy, it is my pleasure to turn the stage over to you. And this button makes it go forward. Okay, and I will get out of your way. Okay, thank you.
Okay. Can we get my slide? Oh, my slides are up. They're not there. Okay. Well, thank you. I'd like, of course, like to thank the committee for giving me this award and my nominators, Christian Genet and Erica Moody from McGill. Great friends, and it's very touching that they went to the work to send all the papers in to nominate me. And of course, I'm absolutely delighted to win it. No matter what you call the lecture, it's awfully hard not to look at the list of people that have gone before and feel quite intimidated. And I wanted to highlight two very special people who've given this same lecture at JSM. David Cox gave the Fisher Lecture in 1989 in Washington, D.C. And he would have used an overhead, he did use, I was there, he used an overhead projector. Not this one, this is just a clip from somewhere in Google, because his transparencies had two words in the middle, and then he would talk for 10 or 15 minutes, and then he'd peel off that piece of plastic and put another one down that had 2 or 3 words on it and keep going. He always said he liked this picture because it has behind his shoulder, it has the adjusted profile likelihood that we worked on in the mid-'80s. And when I had to send in a professional picture some years ago, I tried to duplicate it. I wrote the same formula on my whiteboard and had it taken because he said he liked it. As I mentioned, it was in Washington, D.C., and this is a photograph of the Canadian Embassy down the street. I couldn't resist. The next year, the Fisher awardee was Don Fraser, my husband and life partner, and he gave it in Anaheim, California. And the circumstances were quite different. He delivered it from a Mac 2 CI, which we actually carried on the plane to California. You could do that back then. We were assured they would have a Mac 2 CI there, but we didn't trust the system. And he made his slides using MacroMind Media Director version 1.0. And this is a snapshot of one of his slides. It looks absolutely blurry and funny. I don't remember it being this blurry at the time. I do remember that we were both very nervous about the presentation. But I do have a video recording of it. From that, we have I'm not going to play the whole lecture, of course, but I wanted to show you a little bit of it. So let's see if it'll play. What he's drawn here are 3 significance functions, and I'm going to describe what those are in a minute. But the point is that they're all a little bit different from each other, and they're essentially recording a set of p-values. And in a minute, you'll see his new third-order calculation that he was promoting at the time, and that's the red line that appears, and it's kind of in between the 3 first-order methods from standard asymptotic theory. And now he's going to draw the exact curve over top of the others, and it essentially blacks out the red line, and that was his proud moment showing how accurate the new method was. Now in those days, you had a year's heads up for the Fisher lecture. Now you have about 4 or 5 months, and he spent most of the year preparing this talk. And he was, all these curves that are seemingly drawn as you go is just a swipe right. The curves are already sitting there and they're just being unveiled from the left to right. This was the first lecture I'd seen at a major conference. I think maybe the first one that was given in statistics at a major conference that used the computer. Although I had 4 months and advanced technology, I wasn't able to do as good animations as he had, but I did try to do a bit. Okay, my talk is in 3 parts, and I'll first review a little bit of likelihood inference, something I've spent most of my career thinking about. And then I'll talk about the discontents. Discontents is I like the sound of the title, but what I really mean are extensions, innovations, things that one needs to be careful about. And then I'll talk a little bit about the intersection between theory and applications. So we won't have too much math in this talk, but I wanted to set up a little bit of notation. So we're all statisticians. We're comfortable with models and data and likelihood functions and log likelihood functions, and I just put out the equations that define them. The model is for the data y, and theta takes values in some parameter set, and we would like to know the so-called true value of theta. We have a collection of data in many of the things I'll talk about. They would be independent, but not always. And the likelihood function is simply the joint density of that vector of observations thought of as a function of the parameter. And it's often convenient to work on the log scale. And you will have computed maximum likelihood estimators or had the computer do it for you. It's simply the parameter value that makes your data the most likely under the model. And of course, we usually have several parameters to deal with, and those curves that were drawn in Don's picture only involved one parameter, and they were actually based on not the likelihood function, but the profile likelihood function, which is when you maximize out the parameters you're not really caring about in order to focus in on the parameters that you do care about. But I've dropped the y from this L profile term. It doesn't have a y argument in it. Of course, it depends on the data, so it's a little bit incorrect to leave it out. But the point is, it's not the joint density of anything. It's just a function that we got by maximizing some of the arguments. So it's not exactly the same as the likelihood, but it has many of the same properties. This was Fisher's innovation 100 years ago, and I had occasion through the spring to go back and read much of his work on this topic, and it seems to come across that he's absolutely convinced that this is the answer to everything. Of course, it's much more complicated than that, as we know, but that kind of conviction, I think, helps one to develop new ideas. And I've just drawn two pictures here based on some data that I will tell you about in a minute. I've drawn the density of y for fixed theta value. I picked theta equals 0. And then beside it, I drew the likelihood function for theta for a fixed value of y. I chose y to be 74. And the curves are not identical. I picked a poor example because the sample size is large. So they look more similar than they maybe would normally, but they're not identical. And in particular, the scale of the likelihood function doesn't really mean anything, because it's just proportional to the density, and densities could be measured. You could measure y, or you could measure a one-to-one function of y, and the likelihood function wouldn't change. So the actual scale of the likelihood doesn't mean anything, and it's customary to rescale it so that it's maximized. It takes its maximum value of 1 at the maximum likelihood estimate. Okay, how do we use it for inference? We use the log of the likelihood curve. So now I've taken the same data and just plotted the log function. And we typically either look at the maximum likelihood estimate, which is defined by the red line there, and attach a standard error to that. And the standard error is determined by how peaked the log likelihood function is at the maximum. So if it's very tightly peaked around the estimate, then we'll have a small standard error, and if it's kind of flat like this one is, we would have a large standard error. Of course, that's relative, but we know how to do those calculations. For this particular example, the 95% confidence interval is minus 0.75 and plus 0.03. The other option is to compare how high the likelihood function is at its maximum to values of theta that are near the maximum. So we can look at the distance between the top of the likelihood curve and some line across the middle of it, and that defines another confidence interval, slightly different one, for theta, based on an approximation to the distribution of that statistic, the likelihood drop. And in this case, that gives a very slightly different interval, but essentially the same information. Now, I lied. It's not actually the log likelihood function of a single parameter, but it's actually a profile log likelihood for a log odds ratio. I've called it psi here, but in my plot I called it theta. And it's based on a simple 2-by-2 table, so we're comparing two binomials. And the odds ratio is the parameter of interest, and the nuisance parameter is the parameter that determines the other probabilities. So we have two binomial probabilities. We're interested in knowing if the odds ratio is 1, and we have a nuisance parameter that's a kind of background rate. And for this particular table, which came from a clinical trial that was published about 2 years ago, comparing a randomized clinical trial that compared two treatments for sepsis, the p-value didn't quite make it past under 0.05, and so the authors concluded that the new treatment wasn't better than the old treatment. And there was quite a bit of discussion about this afterwards, because, in fact, after I've showed just the 2-by-2 table p-value, which is 0.07, but after you adjust for the covariates that they used, the p-value is 0.06, so it's pretty close. And so somehow this dichotomization was a bit misleading. Here's a completely haphazard selection from the recent literature to try to convince you that lots of people write papers where likelihood plays an important role. Of course, I looked for the ones that had likelihood mentioned, but it wasn't hard to find them, and there's many, many more. There's a recent paper in JSM about partially observed epidemics and how to do inference based on the likelihood function. A paper in the Annals of Applied Statistics on bacterial identification. A likelihood-based model selection method for stochastic block models, important for the analysis of networks. A recent discussion paper in Series B on graphical modeling for extreme values and how to do inference based on approximating likelihoods for that. A nice paper from about 10 years ago by Chang and Shang on maximum likelihood empirical Bayes. I'm trying to convey, and I could have had 30 more, that there are a lot of problems to be solved in likelihood. I've shown you the introductory part of it with the drop and the distance from theta hat left and right, but there is quite a bit of rich structure in looking at statistical problems this way. And why is this? Well, I think it's because essentially if you take a likelihood approach, it means you're putting modeling first, because the likelihood function is proportional to the density for your data. So you have to sit down and think, well, what's a plausible model for my data? And that sets you on the path of a kind of statistical theory. And likelihood provides a very, I don't know, familiar, useful, practical way to do that. In particular, it immediately gives you summary measures, as I've just showed, the maximum likelihood estimate or the likelihood ratio statistic. If you use Bayesian arguments, you can convert it to a probability. It's often used in a setting where you penalize the likelihood in order to avoid overfitting. And as I mentioned, as Dawn talked about in 1990, it can be converted to a significance function. And I'm going to just leave the others for later and talk a little bit more about how we get that curve that was drawn in Dawn's picture. It's just a slightly different way of looking at inference. On the left-hand side is the same log likelihood function, and on the right-hand side is the p-value function for this particular data. And I drew a line across at 0.975 and 0.025, and that determines the confidence interval. This is now for the log odds ratio, so 0 is the point that we're kind of looking for, where, of course, the authors or the investigators are hoping that this two blue lines don't include the value 0, and then they have a statistically significant result at level 0.05. But the p-value function tells you, in a sense, a bit more, because 0 is way over here in the corner. I mean, it is within the 95% confidence interval, but somehow the fact that it's so close to the end must be telling us something, right? It's conveying a notion that to me, it's somehow more informative. It seems much more plausible that we could be on the border of significance. And of course, if we change the significance level a little bit lower, we would have a statistically significant result. So it's kind of, by providing the whole function, you allow the reader to make up their own mind about the results of the experiment. And this is based on the usual limit theory. I've drawn the p-value function based on the likelihood ratio statistic, the blue one. And it would normally, the drop is approximately chi-squared distributed with 1 degree of freedom because we have one parameter. So if we take the square root of that, we'd have a standard normal. So all I've plotted is the normal CDF. I didn't plot the red one, I only plotted the blue one. And that's the significance function, that's it. It's just the normal CDF of the approximately normal variable, but it's plotted as a function of theta, and the data is fixed. So it's just an inversion, in a sense, of the density function. Now, you might rather convert likelihood to probabilities. That's certainly what our students like to say, right? And investigators that we work with as well, they often misinterpret the p-value as the probability that the null hypothesis is true or something like that. Or you might want to look at the back at this picture and think, well, the probability that theta is bigger than 0 is actually pretty small. So we can say that there's pretty strong evidence here that that there's a negative log odds ratio and in this case it favors the treatment. But if we really want to say it's a probability, we need to put a prior in because the likelihood is not a probability. And that particular 2x2 table was reanalyzed by the original authors using a series of priors. I've just shown you two of them here, an optimistic prior and a neutral prior. And now they really can say that the little tiny area that you see to the right of 1, they've done it on the odds ratio scale, this little tiny space here, that's the probability that theta is bigger than 1. And that's pretty small. So they have somehow, they can stay with, based on this prior, we can conclude that the probability that theta is less than 1 is, I think it's something like 92%. And that's based, of course, on putting in a prior function and multiplying it times the likelihood and then dividing by the normalizing constant. And again, in this problem, we have two parameters, so they actually would have used the marginal posterior probability for the odds ratio, which involves integrating out the other parameter. Of course, this, I'm sure, is familiar to many people in this room. It's just maybe helpful to fix the notation. Okay, so that's the background. Where do we go from there? Well, there's lots of times where this rather simple picture that I've painted doesn't quite apply. There's lots of challenges to using it and some strategies for overcoming them, and I'm going to talk about some of them now. One challenge is the usual regularity conditions. I'll come back to that in a minute. Of course, nowadays we work with very high-dimensional parameters and with big data, so sometimes computing the likelihood is very difficult. The model might be wrong, and then there we are blithely going along, fitting things and making conclusions based on something that's not suitable for our data. And a reminder, it's not a probability. Some of the strategies that have been developed by many people over the years, new asymptotic theory, other forms of likelihood, functions that are kind of like a likelihood but not quite, semi and non-parametric approaches, and a kind of objective Bayes approach, which tries to convert a likelihood to a probability without injecting subjective information about the parameter in the form of a probability distribution. So I'm going to talk about each of these in turn, but I hope it won't take too much time. This clock is counting down, so I guess that's my, okay, so I should have time for that. So let's look at the usual regularity conditions. Here's a little picture from an old paper of mine that I wrote with Harry Joe in 1985. This was a really interesting problem, very fun to work on, that David Cox suggested. He just kind of wandered in to the office when I was a postdoc, or maybe visiting Imperial, I'm not sure, probably when I went back to visit, and wrote something on the board. And then he had quite a genius for suggesting problems that were solvable, but just solvable. And in this case, it was estimating the number of faults in a software system. And I think he had actually been asked the question by an engineer. And what we found was that there were 3 different scenarios for the parameter of interest. The likelihood function looked like one of those 3 curves. And of course, the one I showed you before was a lot more like case 3, the one on the far right. But in many examples, the maximum was either at the boundary on the left or the maximum was infinity. So you would either say the number of faults was equal to the number you'd already seen, or you would estimate it to be, well, I don't know, there's a lot. Or if you were lucky, you might be able to get a bounded confidence interval. Now, this comes up in many more familiar examples. Many of you may have worked with variance component models, in which case the variance, for example, between the groups, you might be interested in testing if that's 0 or not. And that parameter then is on a boundary. So you have to think about what kind of inference you can do if your likelihood function looks like the curve on the left, for example. In logistic regression, if your students might hand in some R output with a list of coefficients, and one of them is 10,775,000 with a standard error of 20 million. Well, that's because they forgot to notice that the algorithm didn't converge, because most likely there was complete separability, so that all the ones were on one side of a value of x and all the zeros were on the other, or some linear combination of those. And in that case, the estimate the likelihood function looks like the one in the middle, and you don't get a finite maximum likelihood estimate. Another type of regularity is another type of boundary problem comes up in particle physics, where after very much data manipulation that I've never understood, they insist that they have a single count from a Poisson with either has a mean b or a mean bigger than b. And that's the background plus the signal. And their interest is in testing whether the signal is present or not. So some of the strategies that are available are, well, change the asymptotics. So in the variance components example, the likelihood ratio statistic, the blue drop that I had a picture of earlier, that has a distribution as a weighted sum of chi-squareds, not as a chi-squared distribution in the limit. And it's a little bit complicated to work with, but we know what the distribution is. So that's one possible strategy. In logistic regression, when there's complete separability, one possibility is to work with the exact conditional likelihood for the parameter of interest. And then, of course, the confidence interval for that will still be one-sided. You could only say that you would be 95% confident that beta was greater than some number, but you wouldn't be able to put an upper bound on it. But that, I think, is perfectly sensible in that setting. The data aren't, there's not enough data to discriminate large values of beta. But another approach that's maybe more useful if you need to take those estimates and put them into a different summary is to adjust the maximum likelihood equation. In this case, Firth proposed adjusting the equation by debiasing it, and that also allows you to obtain finite estimates in the logistic regression setting. In the background and signal case, Don and I were convinced that the significance function is quite satisfactory. It just means that there will be some p-values, there will be some weight attached to values of mu smaller than 0. And the physicists are very uncomfortable about that because they know that it has to be bigger than 0. But in terms of looking at the whole function, you can say, well, how close is it to 0, and how worried should we be? And I don't think there's any problem really in using kind of standard theory there, but I'm not sure that the particle physicists would quite agree. Another class of problems, still in the class of regularity conditions, sometimes the parameters aren't identifiable. And here's the very simple mixture model. You may have worked with them as well, and this is one of many, many more complex ones that have been proposed. But immediately, of course, if the mixing probability is 1 or 0, then we only have one distribution, not two, so we don't have two thetas. Similarly, if the thetas are equal to each other, then we can't determine the pi, but maybe that's a less serious problem. But you could imagine many variations of this where the parameters are simply not identifiable. Another place where the parameters are not identifiable are change point problems. I didn't write down an equation. I took this lovely picture from Peter Guttorp's paper in 2014 of a climate series from simulations. Of course, the interest is whether there is a change, and these are the temperature anomalies, I think. And so whether there is a change in temperature anomalies in the last years. This was from 2014. I think we're now quite convinced that there has been. But in a general regression setting, if you thought that the slope was one value and then it changed at some point to another value, well, if it doesn't change, then you won't be able to identify those two slopes. So there's a kind of confusion of parameterization. You have maybe three parameters, slope 1, slope 2, and the change point, but they might not all be identifiable from the data. Again, one of the approaches that's been quite successful is to try to figure out new asymptotic arguments that apply to essentially the maximum likelihood estimators or the likelihood ratio statistics. And these tend to involve the maxima of Gaussian processes, that is, the distribution of the likelihood ratio test is the distribution of the maximum of a Gaussian process, or a Gaussian process squared, I guess. There's a really lovely explanation of this in Cox's book, Principles of Theoretical Statistics from 2006. He has a whole chapter on when likelihood goes wrong, beautifully written, very concise, framed not very differently from what I've done, but I've highlighted slightly different things. But he explains in about 1.5 sentences why the answer has to involve the maximum of a Gaussian process, and it's worth a read. I highly recommend it. There's a tremendous amount of very interesting theoretical work on high-dimensional parameter spaces going on in the theoretical literature right now. I just picked one of many possible examples. Suppose we have lots of 2x2 tables, and we think that they have a common odds ratio. So in every 2x2 table, we'll have a nuisance parameter for that other probability, because there's 2 binomials, right? We're only specifying one of them. And as we accumulate more and more of these nuisance parameters, the maximum likelihood estimate fails us. It doesn't converge to the right value. In fact, it's much too big. It converges to 2 psi, twice its true value in the simplest case, where we just have one observation on in each group. The problem is the parameter space dimension is growing with the sample size, and that's not allowed by the theory that gives us those nice plots that I showed you before. But there is a workaround. There's a very nice strategy, also, again, proposed by Cox in '58, but developed by many people, and a version of it proposed by Bartlett much earlier, actually, which you will probably also have been familiar with in practice or in theory. If we condition on the marginal totals, then we get rid of the nuisance parameter in every single table. So we can take the product of those conditional densities, and essentially the sum of all the 1-1 entries of all those 2x2 tables is conditionally sufficient for the parameter that we care about, in the sense that the conditional likelihood only depends on the parameter we care about, and we've managed to finesse those infinitely many nuisance parameters. That's the basis for Fisher's exact test, and many similar models admit conditional or marginal likelihoods of this form, the idea being that you take your complicated model and try to factorize it into 2 pieces, one that captures the parameter that you are interested in, and another that doesn't have any additional or very little additional information about the parameter of interest. And Heather Batty has some interesting, very recent work with David Cox on trying to find this structure directly from the model. So in those particular special cases, and I could have listed many more, we can kind of have a lot of nuisance parameters, but we have a way to get rid of them that's kind of intuitive. And actually, if you go back to Fisher, he kind of said this, although it's a little bit hard to see. He would say something like, well, if you have a complicated problem, you just find something that measures the parameter. And he didn't spell it out, but it was a kind of, intuitively, he could see that you could eliminate these, what we now call nuisance parameters, by being sort of clever. So that's fine in the settings where they work. The work that David and I did in the mid-'80s that we had the picture of at the beginning was to try to show how you might approximate this approach by taking the profile log likelihood, that function where you just maximize out the nuisance parameter. And we proposed adjusting it by a term that depends on a determinant, and the determinant is a determinant of a matrix, and the matrix is the second derivative of the log likelihood with respect to the nuisance parameter. So it's a piece of the Fisher information matrix, and if you subtract that piece of the Fisher information matrix from the profile likelihood, then you get something that's pretty close to a conditional or marginal likelihood function when they exist. Now, in this equation, I have an extra term called A of psi that we actually didn't use, so I should cross it out. But if you don't have this extra term, then this right-hand side is not parameterization invariant. And Barndorf-Nielsen and Don Fraser both had expressions for this extra fine-tuning that makes it invariant to reparameterization. But unfortunately, that term is quite hard to compute, whereas the first two are really relatively easy to compute. So what we discussed in the original paper was that since we knew it wouldn't be parameterization invariant, we would try to make the nuisance parameters as non-influential as possible, and we did that through a notion of orthogonal parameters. It turns out that you can take this, if you don't want to take the profile, you could take this adjusted profile and turn it into a significance function in very much the same way that I turned the simple profile likelihood into a significance function. And that's really what Don was talking about all those years ago. He was doing it in fairly simple problems, but over the years, there's been a theory developed to do it in more complicated settings. However, these approximations all actually rely on fixed dimension. So in principle, we want things to work when P's going off, the dimension's going off to infinity, and we've got something that works for P pretty big, but not going off to infinity. But there's some quite fascinating new work on when P really does go to infinity. And in linear models, that was pioneered by Donahoe and Johnston and Bickel and collaborators, El-Kharawi and so on. But in nonlinear models, like generalized linear models, Pragya Sur and Emmanuel Candas have a series of papers showing that you really do need a new theory if you want P to grow with n at a certain rate, and you're not going to take the approach of trying to be clever like Fisher, but you want to apply a likelihood theory. They showed that the profile log likelihood ratio statistic doesn't converge to a chi-squared 1 or a chi-squared k if we had k parameters, but some multiple of that, and you have to figure out what the scaling, what to put in front of it in order to rescale. And this picture on the left from their paper shows the p-values if you don't rescale on the left, and the p-values after you use their new theory on the right. And in the middle is a kind of intermediate case where they did a partial correction using Bartlett factors. This work is hard and it's a little bit specialized, and it's those two parameters that you see in front of the chi-squared 1 are characterized by studying the optimization path. So it's rather involved and maybe not a little bit hard to implement in more complex problems and not exactly clear how well it would extend. And of course, there's many other people working on this problem because it's so fascinating. Fan et al. Have a more general a set of models. They look at all generalized linear models, and they concentrate on the correct asymptotics for the maximum likelihood estimator. In both cases, if I'm remembering correctly, the results are specialized to testing only that the regression parameter is 0 in logistic regression, and the x's are random. So there's still a lot more work to be done to kind of see what's happening. Yesterday, David Banks in his Deming lecture said there were 2.5 theoretical advances in his career. I'll come back to that point later, but this is the half. There is a kind of funny phase transition in asymptotic theory between getting the usual limits and then suddenly getting different limits. And my PhD student working under my supervision, Yanbo Tang, took on the challenge that I said, well, when we have a set of data, we have lots of parameters, we have a certain sample size, how will we know if P is going to infinity or not? P is 400 and N is 600, or P is 400 and N is 800. Is that bad or good? So he tried to analyze the higher order asymptotic theory that I mentioned that Don and I have developed in the setting where P is increasing with N, and has some interesting preliminary results that show that you can let the dimension grow at about n to the 1/3. There still will be a phase transition, but I'm not sure how we would analyze theoretically that phase transition. I think that's an interesting open problem. These two pictures are from Yanbo's thesis and from a paper we published in Series B. On the left is the first-order normal approximation, and on the right is a higher-order approximation, and he's showing the distribution of the p-values for testing the null hypothesis. They should be uniform 0, 1, right? He's showing that against the scaling of the parameter dimension with the sample size. So you can, the bottom line is that they're more uniform on the right for longer. It falls apart over in the very far right, but up to a scaling of 2/3, that is, p is 2/3 of n. Sorry, it's n to the 2/3. You can see that the p-values using the higher order methods are actually fairly well distributed according to a uniform and improve on the first order methods. So the theorem only applies for n to the 1/3, but it looks like it might work better than that, and we don't know why, and we don't know how. Okay, I have 2 more challenges, and I think I do have time to look at them briefly. So, of course, I've had many questions over the years about this particular point. Anytime I give a talk on likelihood, someone in the audience usually says, yeah, but what if the model is wrong? And well, there are some strategies for that as well. As before, develop a new theory. Cox did this in 61 and 62 with his theory of separate families. So the idea is that you're still fitting that f of y theta to your data, but the true distribution isn't that at all. It's something else that you don't know. And then you can show that the maximum likelihood estimate converges to the parameter value that gets you as close as you can to the true distribution in the Kullback-Leibler distance sense. And from that result, you can then go on to establish the limiting distribution of the estimate and an estimate of its asymptotic variance. And this has, there's quite recent work by Van Steelant and Dukes on exactly this point, assumption lean inference for generalized linear models, where they basically develop a new theory of asymptotics and estimation that applies in a more general setting than assuming the model is correct. Roughly speaking, you get a limiting normal distribution for the estimate, but the asymptotic variance is larger than it would be if you had the correct model, which kind of makes sense. And there's that sandwich variance formula that you may have heard of that can correct for that. Another thing to do if you're worried about the model being wrong is not to be so prescriptive in your model. So you could make it more flexible. And again, a most famous example of this is the proportional hazards model, where we want to model the hazard over time. I've modeled time with y here, given some covariates that influence the hazard function. And so the model that Cox developed was to imagine an underlying hazard that gets multiplied by a factor related to the covariates, and then showed, so the model is kind of a simple and natural one, but the breakthrough was to show that you could estimate the betas without worrying about the lambda 0. So it's a semi-parametric model because we don't have to specify the underlying hazard function, and we can still estimate the effect of the covariates on the hazard function without actually worrying about its form. That can be justified as a partial likelihood, although, in my opinion, partial likelihood is a somewhat vague term that was possibly invented to justify the proportional hazards model. I'm not sure, but I feel that there's some overlap there. But Murphy and van der Vaart in 2000 also showed how it could be interpreted as a certain type of semi-parametric profile likelihood, and showed that the asymptotic theory that I was talking about at the beginning still holds. You could go fully non-parametric. It's hard. It's not for the faint of heart. Empirical likelihood developed by Owen is one example of a kind of non-parametric likelihood. There's lots of very interesting work now on constrained estimates of densities. You can't just estimate the density without putting some conditions on what it might look like. So it might maybe have this monotone or has certain properties, and then you can estimate it non-parametrically, and the asymptotic theory needs to be developed in that context. Computational intractability, I think maybe this was part of David's motivation yesterday for wanting us to look at things a little bit differently. There are many large and complex data sets for which the likelihood function can't really be computed in a reasonable length of time or just can't be computed at all. And remember, I was talking about maximizing some of the parameters and keeping some of the parameters fixed, and that has to be done for several values of the fixed parameters, so that's a lot of likelihood calculations. Latent models are a primary example of this, where we have some relatively complicated model given, or possibly relatively simple model, a parametric model given some covariates, some hidden variables, but once we integrate out the density of those hidden variables, then we're in lots of trouble because we have a high-dimensional integral before we even get started, and then we want to go on and find its maximum over theta and so on. Spatial processes are full of these examples, network models, multivariate extremes, and the agent-based models that David mentioned yesterday. One strategy that's proved popular for these types of problems is to replace the likelihood by something a little bit simpler. So often these models are developed for responses that have a lot of complicated dependence, and that integrating over Z creates the dependence between adjacent points on a spatial lattice or adjacent points in time. And that complicated dependence could possibly be a little bit ignored in some settings. So the way I've ignored it here is to imagine that instead of looking at the full joint density for the response, we would just look at the bivariate marginals. And if the theta parameter still has some meaning in the bivariate marginal, we could imagine using that as a kind of likelihood-like function. That was first proposed, I think, by Julian Bisag in 1974. He called it pseudo-likelihood. And Bruce Lindsay wrote a very elegant series of papers on composite likelihood and its asymptotic properties. And finally, a reminder that likelihood is not a probability. It can't be integrated without introducing some prior for the parameters. And in these very complex models, the priors can be quite difficult to specify. So one strategy that's been developed in the O-Bayes group, the objective Bayes group of the Society for Bayesian Analysis, is to essentially find a prior we can all agree on. Sometimes these are called objective, sometimes weakly informative. The point that I think needs to be emphasized is that that will be fine, but we need to check that the inference methods from the posterior do have good performance under the model. Otherwise, the prior is injecting information into the problem that may not be appropriate, or that we may be giving us answers that in the long run would not be reliable. And this needs to be checked in every application. This is not a particularly popular opinion among Bayesian statisticians who would, I think, perhaps argue, well, I'll use a prior that I think is quite plausible, and then my inference method is very coherent and well-defined. I know exactly what I'm doing and know what my output is. And as long as I check that things aren't too badly off, it should be fine. But when you say check that things aren't too badly off, I think then you have to go back to the sampling model and see if your posterior intervals do really have the probability in the sampling model that you're claiming for them. I have one example that has emerged recently about this, and it has a lovely romantic name called satellite conjunction analysis. But that really means estimating the probability that two satellites will collide. And there's a lot of satellites up there now in low Earth orbit, so this is a very serious and pressing problem. And it essentially boils down to inference for the length of a normal vector, which is a problem that goes all the way back to Stein. And the problem is simple to state. We have a whole bunch of independent observations, and everyone has a different mean and the same variance. And if you use a flat prior for all those different means, but you want the marginal posterior for the length of the vector, that will not have good performance in repeated sampling from this model. And you can easily show that the discrepancy between the exact p-value and the Bayesian posterior probability is a function of how many means you have. It grows linearly with the number of means. Now, we could construct a prior targeted on that, of course, but that wouldn't be the flat prior. We'd have to say, oh, we want to analyze the length of the vector, so I'm going to now redo my problem knowing that that's what I want to do. But if you, this is a simple problem, we just have a bunch of normals. If you could imagine one of these complex spatial processes, and then you're not really sure which parameter you're going to be looking at the end, maybe you're going to be looking at 7 or 8 of them, so it's not quite so simple in that setting. So in this is a bit of a toy example, but as I say, the connection with the satellite conjunction problem is kind of interesting. Here's my picture. I've used this in many different talks to convince you that this is an issue. And it's just a restatement of the theorem that Stein proved in '59, but the blue curves are p-value functions, that is, they're significance functions, and the red curves are posterior probability functions, and they're diverging from each other, and the different types of lines is how many means we have. So the two solid lines, there's k is equal to 2, there's 2 different means, and the next pair of dashed lines, k is 5, and in the third pair, k is 10. So a Bayesian probability would be computed, say, if we had 10 means from this curve, but the right answer would be computed from this curve, because the flat prior for all those means gives provably the wrong answer for the length of the vector. It's just the wrong prior to use. And it's a warning that priors that seem innocuous are not, as soon as you start integrating. Okay, this is a slide about the discussion about this problem in the Proceedings of the Royal Society, but I think I'll skip over that. Okay, so I had a lot of trouble focusing part 2 of my slides for this talk, because there's many, many, many more pages and books and so on, and it's I have to strike a balance between a high level touching on things and trying to convince you that there's some interesting work underneath it. But along the way, I used a lot of adjectives in front of likelihood, and at least those 5: marginal, conditional, partial, composite, and pseudo. And there's a bunch I left out. Oh, I did say empirical. There's a bootstrap likelihood, simulated likelihoods, sieve likelihoods, penalized, quasi, and so on. The common theme, to provide inference strategies with well-understood properties. So it's a kind of place to start. If we have to do every applied problem anew, we don't have a subject anymore. I think machine learning is facing a little bit of this problem now. And certain aspects of data science, that is, you have this huge mess of data that's coming in really fast, and the collaborator wants something done now. And if you have to sit down every time and reinvent something, it's just not very efficient use of all our resources. So somehow focusing on statistical modeling and likelihood functions gives us a kind of something to get started with. And it enables us to stand back a little bit from the specific problem that we're looking at, because the theory provides guidance for a range of similar applications. So I'm going to talk now about applications, but really I'm going to indulge myself on what's my favorite part of giving general talks, and that's looking at statistics in the news. I was lucky enough to be forced to give a freshman seminar many years ago. Many years ago, too many to count. And the topic of the seminar was statistics in the news, and it's become an absolute hobby that I can't give up. I spend inordinate amounts of time digging out things from recent news and science articles and so on, and digging into the background. So here's something from The Economist from a few weeks ago. Evidence for behavioral interventions looks increasingly shaky. Behavioral interventions are nudges, and in fact, I think the cover of The Economist, or one of the mentions of this article, said referred to nudge theory. And the subtitle for this article is that the academic literature is plagued, I tell you, plagued by publication bias. So, of course, there's a source, there's a paper that the Economist article writer would have looked up, and it's from the Proceedings of the National Academy, and it's a meta-analysis of choice architecture interventions, which sounds a little bit more academic than nudging, I guess. And so but what was kind of interesting about this particular article, which was published in December 21, is this past July, I think a week before The Economist, there were 3 letters that were published in, this is too small for you to read, but 1, 2, 3 letters to the editor, all published together. First one, no reason to expect large and consistent effects of nudge interventions. The second one, left truncated effects and overestimated means. The third one, no evidence for nudging. And then the hapless authors got to reply to all of these. Now, in their defense, probably there wouldn't have been so many letters, but they put the data all on the Open Science Foundation webpage, and it's good quality. It's the code is there, the data's there, and it does download, and you don't have to do any fiddling around, which is pretty rare, actually. Even when people say they publish all their data, they rarely do. So the data's all there, so these authors could be armchair quarterbacks and see what to do. But here's what the original people did. They found 440 different estimates of effect size from a smaller number of unique publications. And they used a random effects model, and they had many fixed effects moderators for their secondary analysis. And they tried to assess the publication bias. Remember, the headline is plagued by publication bias. So they plotted the standard error versus the effect size, and they referred to Egger plots and Egger's test. And I was really happy to learn about these because Marlene Egger was a classmate of mine at Stanford back in the day. So it was nice to see her name again. So this is a sort of thing you may have seen in meta-analysis plots before. I find it a little bit confusing, to tell you the truth, but these are all the effect estimates, the 212 with their standard errors. And the point is that there's a lot out here with kind of long standard error bars that have larger effects. And the Egger plot is exactly to show that the standard error increases with the effect size. It's a little bit confusing to see that on this picture because the standard error here is going up in the down direction. So this is 0 and this is 0.6. So you can see there's a line there, and it's basically mean that the standard error is increasing with the effect size, and that's a kind of indication of some publication bias. Their overall estimate of effect was 0.43, and they said that that was an interesting and important result in spite of the publication bias. So the authors themselves were kind of arguing that there's evidence in this meta-analysis that nudge theory is effective, but they did acknowledge that there could be some publication bias, but they insisted that in spite of that, they felt that there was an overall effect. And the letter writers writing back were saying, no, you're wrong, because you didn't correct it the right way, meaning you didn't correct it my way. The one publication said that publication bias was not handled properly, and their argument was that they have a newly proposed bias correction technique, a robust Bayesian meta-analysis, and that's the approach that they recommended. Another set of authors adjusted for publication bias in a different way, following some suggestions in the literature, but made the quite reasonable point that the average effect size is not terribly informative, given how much variation there is from study to study. And there was a very nice graphic in the third letter, which just showed how much indication, evidence there could be of publication bias in the different domains. That this is subdivided according to behavioral domain. But I think that this picture is just much more compelling than the picture I showed you of the curve going up, the cumulative distribution. This is just showing the distribution of the different effect estimates, and you can see that there's a cliff, especially in some disciplines, at the uninteresting values. So that is, I think, a sort of, if you saw that first, you would say, oh yes, obviously there's publication bias. So this is fun for me. I like looking at these sorts of things, and I like digging through the supplementary material and so on. But it does have some connection to what I've been talking about, because the first letter said, oh, we're going to use robust Bayesian meta-analysis. And so their picture looks like this, and each of those points is a posterior probability, or a posterior probability interval with a posterior maximum posterior estimate in the middle, so to speak. And when they combine it, they get something rather small and actually not very interesting. Remember, the one that I'd circled before was 0.43. That's kind of more interesting to look at, and this one is essentially 0. So they're providing model average to mean effect size estimates with their posterior intervals. I don't know what prior they used. I don't know what makes it robust. I didn't go into all those details. The other letter writers did non-Bayesian adjustment and got similar results, so they're not terribly different. But I think it's of interest, although the answers are possibly not very different here. I've seen this in several cases where someone disagrees with the result and they reanalyze the data using a completely different method and then say, well, obviously our results are better because we used a better method. But that doesn't necessarily get calibrated in the way I was talking about before. So I think it relates back to the 3 red curves and the 3 blue curves. For this data, perhaps it doesn't matter, but I think it would be of interest to think about it from that point of view. You gotta love being a statistician because you learn something new and then it comes up everywhere. So Thomas Lumley tweeted about a science and medicine in football, and also looking at why you should be wary of results that are too good to be true, why that new science-backed supplement probably doesn't work. It's a story about publication bias. You've probably already guessed that, the bias for statistical significance in sport and exercise medicine. This is a preprint from the Open Science Foundation that hasn't yet been peer-reviewed. Their picture is much more easier to read, I think, than the original ones that I was showing you before. They looked at a whole set of Z values from numerous publications and found the missing middle, which is not too surprising, I guess, given the lead up to this. Now I'm moving on to a different article. And this was a nudge article, actually, that came out in April in Science. Kind of interesting and also caught my attention because one of the authors is from the University of Toronto. How safe are safety messages? And the research by the pair, Hall and Madsen, suggested that displaying traffic fatality numbers in traffic safety messages is associated with an increase in downstream fatalities. This particular discussion of the paper by Ullman and Chrysler said this seems inconsistent with other research that has found that these displays are mostly ineffective, which makes you wonder why they put them up if they found they're mostly ineffective. But this is rather more serious, right? There's an actual increase in fatalities downstream. And the authors thought that the issue might be one of kind of cognitive overload, like if you're trying to process too much information from one of these highway screens, maybe you're not paying enough attention to your driving. So that's a nudge that seems to be going in the wrong direction. They had a very interesting natural experiment because in Texas, all the data comes from Texas, they post messages about fatalities in 1 week of every 4. And so they could use the other 3 weeks as controls. And they did a lot of adjustments for weather and time of day. and so on, and concluded that accidents increased by approximately 1.5% in the weeks when the messages were displayed. Although when you drill down, it's a little bit less clear because here's it's hard to know without looking through, all the details, but the little table that I've put in the corner, the line you want to look at is the first one, campaign week times post. So that's meant to be the coefficient that measures the increase in percentage crashes per hour. 3 kilometers from the sign, 5 kilometers from the sign is the second column, and 10 kilometers from the sign is the third column. And the first 3 kilometers seem pretty safe because there's no stars beside the estimate. And the next 5 kilometers are the more worrisome ones, where there's it seems to be a statistically significant, rather small, but statistically significant increase in the percentage of crashes. I have quite a few questions about this study, but we don't have time to talk about them today. They said they have 62 million observations, but it was never clear to me from going through what they wrote where those came from. But I did look up, you can find out from the Texas Road Safety webpage that there's about 1 reportable crash every minute. And if you're bored, you can figure out how many minutes there are between, I think they started in 2010 and went to 2017. And I reckon if I did the calculations right, there's about 4 million minutes. So that would be 4 million crashes, and they have 62 million observations. So I'm not quite sure if they maybe counting things a little bit funny. But I'm also a little bit alarmed by the significance taking precedence over the actual numbers. By way of comparison, a light rainfall increases the accident rate by about 25% and heavy rainfall by about 50%. So this is a small effect. These are always fun. This is my last one, diet and health. This was in the New York Times this summer. Is chocolate good for you? And it refers to a couple of articles that were recently published. One was a review of several meta-analyses, and the other was a very large randomized trial. And the table that I've showed here is teeny tiny, is the review of all the meta-analysis, and they were actually looking at lots and lots and lots of different interventions in diet, not just chocolate. In fact, there are just 5 studies that looked at chocolate, 5 meta-analyses that looked at chocolate. So every single one of these little bars is the one you would see at the bottom of the individual publication. They would have several confidence intervals, and then they'd have that little tiny one at the bottom. That's from the result from the meta-analysis, and there's the 5 for chocolate, and they tend to be to the left of an odds ratio of 1, although it's not quite clear that the confidence intervals are too inspiring. The second one was actually a randomized controlled trial, double-blind placebo-controlled trial of 21,000 US adults. It was not a randomized sample, it was a convenience sample. And they didn't test chocolate, they tested a cocoa extract supplement, which is not quite as enticing to have every day at the end of your dinner. They were, I give them credit, they were very careful to note the limitations of their study and the discussion. But here we have this again and again and again. There was no statistically significant effect on the primary outcome. However, cocoa significantly reduced cardiovascular death by 27%. That really sounds like a little bit of p-hacking, I think. But I could see the temptation. This was an absolutely huge trial, and it was expensive, and they wouldn't be able to run it again. And their primary, they argue in detail about how their primary outcome was too vague, and they should have chosen this secondary outcome as their primary outcome, and so on. And they're very qualified, but of course the headline is chocolate good for you in the New York Times? Now, over the years I've been doing this project of digging through the news and just having fun and taking it to the students. Some stories just never die. I'm going to skip that one. And chocolate is a story that never dies. So this is a story from Easter in March 2010 from my local newspaper. Researchers find those who eat 7.5 grams a day have a lower risk of heart disease. And all the way back in August 2005, Can chocolate save your life? Was the headline for that one. Probably not. So it's just kind of amusing to see this come back and forth. Now, these are just haphazard examples from hundreds of similar stories. This is a screenshot of my Chrome browser bar of yesterday, and I had about 4 windows open like this. So I just picked ones that I thought were sort of fun to look at quickly. But what I say is that p-values are everywhere, whether we like it or not, they are everywhere. But I would say also that statistical issues of sampling and bias and reproducibility and so on, they're much, much more prominent in the popular press than they were when I started this some 20, 25 years ago, this project. And I came across 2 very interesting segments that I hadn't known about, but perhaps you did. The Journal of the American Medical Association regularly publishes articles on guiding on statistics and methods. There was one last week on regression models for ordinal outcomes. Very well written, very clear, non-technical explanations for practitioners. Naomi Altman and a team of researchers writes very regularly for Nature Methods, an article called Points of Significance. The Proceedings of the National Academy of Sciences has just convened a statistical panel to start looking at some of their papers. So there's clearly, incredible demand from, I guess I'm preaching to the choir here, but there's incredible demand for statistical expertise from all quarters. And I think that's very, very encouraging for us. And I came across a very interesting article just the other day about, thanks to Twitter, to Statistics and Data Science. This is a blog post by Kapoor and Narayanan about the reproducibility crisis in machine learning. And they're particularly focused on what they call data leakage, which is essentially an overlap between the training data and the test data, or using features that are essentially proxies for the outcome, or using a test set that's totally irrelevant because it's so different from your training set that it shouldn't be used as a test set. And they mentioned there's a much better known reproducibility crisis in research that uses traditional statistical methods. So to summarize, a likelihood function is just a statistical model, but it provides a different perspective on the model. It emphasizes the inverse problem, going from the data back to the model. And theory provides guidance for a range of similar applications. There have been many theoretical advances since Fisher defined the likelihood function in 1922, and especially in the last 50 and even in the last 20. So I have to take great exception with David's comment that there were 2.5 theoretical advances in his career, because we've had the same length of career. And I would say there's very many more. Of course, I'm biased. But I think that looking at the world from a likelihood lens continues to inform these advances. Okay, well, I have to thank Christian, Janae, and Erica again for taking the trouble to nominate me for this award. Unfortunately, they can't be here today. And I also want to thank Heather Batty and Yanbo Tang, who have been holding my hand as I was preparing these lectures and providing valuable advice. But I could fill 10 more MacBook screens with people. I'd really like to thank my teachers from so long ago. It's no one builds a career without getting lots and lots of help along the way, and I've had the great good fortune to interact with many influential and helpful people, and I don't have space to put them all here. But as we know, the best part about any work life is the friends you make. And these are the friends who came to my birthday party in May. So that was it seemed like a fitting place to stop in. Thank you for your attention.
How you going? Let me straighten that mic out for you real quick because what's happening is it's actually hitting your.
Oops. We're happy to take questions. There's 2 microphone stands, one on this aisle and one on this aisle. We'll take a few questions if anyone would like to talk with Nancy. Please, come sit. That was great. All right, I'm going to do this. That's people. There's a lot of movement there. Let's see. I see. All right. I'm going to buy some people. So, what's the greatest highlight of your research career?
Oh my
I'm going
goodness.
to put you on the spot.
Wow, the greatest highlight of my research career. Oh my goodness. Well, I'll punt, because when I interviewed David Cox, I said, "What's your favorite piece of research?" And he said, "Whatever I'm working on now."
So that's,
Yes.
I'm going to borrow that one too.
But I think presenting our paper to the Royal Statistical Society in '87, that was pretty exciting.
Yeah, excellent.
That was really fun. But yeah, that does stand out. And actually, Don's talk in 1990 at JSM, that was quite fun. I have the distinct memory, but perhaps I imagine it, that when that curve appeared on the big, huge screen in the ballroom like this, that there was an from the audience. But I'm not sure if I made that up or not.
1990. And you really carried that on the plane.
We did. We carried our Mac 2 CI on the plane, yes. Yeah.
They were, for those of you who are young, they were pretty heavy.
And our talk was backed up on floppy disks.
Yes, exactly, yes. Exactly. We do have a question, please. Introduce yourself and then ask your question.
Hi, I'm Ed George. Hi, Nancy. Great talk. Wonderful. Just a comment about, right, you talked about in assessing Bayes' methods, the uniform prior in high dimensions, and the Stein problem. But is that a real Bayes problem? Stein was about maximum likelihood. And actually, I think at one point, George Bach said that maximum likelihood was a coward's way of being a Bayesian, using uniform priors. I mean, just for fun, but so.
It's true that Stein didn't analyze it the way I did. He was actually pointing out a problem with fiducial inference. But he showed that the expected value of the point estimate would be too much under that prior approach. But he was approaching it from a fiducial point of view. Right. But the result was the same, but the argument was slightly different.
Although when people talked about it, they said that the Stein estimator dethroned the maximum likelihood estimate. That was one of the big messages. But yes. Thank you.
Thanks.
Thank you. Okay. I don't know if this is, should I put you on the spot again? No.
Sure, I don't mind.
I don't know if there's another question.
Yes.
Let's just see here. I think there's another question coming. Hi. Please introduce yourself and ask away.
I guess I could have just stood up front and asked you. Kathy, Enser, and Nancy, I just want to congratulate you on your award and everything that you've done and just this wonderful talk that you've shared. So, as I shared yesterday, I obviously jump into quite a few applied problems for some rationale, and you indicated that we should always sort of look to the likelihood in the model. And how do you actually decide when you have a new problem facing you where you're going to start?
Oh, that's a hard question, Kathy. How do you decide where to start with a new problem? So I work in theory because it's so much easier than applications. When you start with a new problem, I think there's figuring out the data and where it came from and how it's going, what shape it's in, and whether it's worth the trouble to do something fancy or not fancy. But it's thinking of, say, a genuine scientific collaboration with some people who really want to get the most out of their data they can, then I think you start with the model. And in a sense, you have to think of some plausible way that this data could be modeled. And it might not be the way the data was generated. That might not be so relevant. It depends on the application. It might be other things that could be very usefully deduced by using, say, a simple Poisson model like the background plus signal in the physics problem. And then at that point, I think then from my point of view, you're looking at the likelihood function. And so I would say if you look through many applied papers in statistics, but applied papers like the Annals of Applied Statistics or JRSSC or whatever, they very often start with the model, and they very often either do Bayesian inference or try to do some type of likelihood inference. But there are settings where you can't, like graphical, multivariate extremes, for example, is an area where there isn't really a way to implement likelihood inference yet. There's likelihood-like things you can do, but at the moment it's not really feasible. So it's a wonderful question. Where do you start with a new problem? But that's what keeps us going, right?
Yeah, that's a great answer. And again, thank you.
Yes. Let's thank Nancy again for a wonderful lecture.
Thank you.
So let's give a big congratulations to all the COPSS Awards winners, So let's give a big round of applause, I also want to thank Ron Wasserstein and his excellent staff for the help we received in organizing the COPSS ceremony. And thank you, Ron. And this concludes the COPSS ceremony, and good evening.